For over 2,000 years, humanity insisted that infinity was only potential. So roughly this means that you can add one more, but you can never actually arrive. Aristotle thought so, Gauss just said so, and then Cantor showed up like a boss with a heresy, and we're still fighting about it to this day. So what is infinity, and why the heck is it so controversial? Cantor treated infinities as objects that are completed in and of themselves that you can grab. Now, not only is that nuts, but he then proved that there are strictly more of these infinities than anyone imagined. Kronecker called Cantor a corrupter of the youth. Poincaré called Cantor's work a disease. Cantor then died in a sanatorium. So what the heck is going on? Now, to understand this, we have to talk about potentiality versus actuality. And no, this isn't Deepak Chopra mixed with set theory. The distinction is sharper than it sounds. A potential infinity is a process. Like you keep counting, you do 1, 2, 3, 4, etc. You don't stop. And at no point do you say that you've had a complete collection. You just say that there's always something else I can do. That's called a potential infinity. Now, an actual infinity says that that whole collection exists right there as a single object. Now, what does that mean that you can handle it as a single object? Well, you can examine its properties, you can compare it to other collections, you can then ask difficult questions about its size. You get the idea. Now, Cantor's heresy was insisting on the latter, that you can actually do some math with this concrete object. His first discovery was quite peculiar. There are as many even numbers as there are natural numbers. Now look, over here you have to be specific by what you mean as there's just as many. You also have to be specific as to what you mean by size, and mathematicians call that cardinality. Two sets are of the same size if you can pair them up exactly. You can think of it like how kindergartners are in pairs, they hold their pinkies together. Now on screen I'll show you what it looks like with all the even numbers and the full natural numbers. You can see there's a one-to-one pairing. A bijection is what mathematicians call it, meaning you can go from one set to the next and back and not lose anything. Nothing's left over. It turns out that the same goes for the integers and the same goes for the rationals, which is quite absurd since the rationals are dense in the real line. But Cantor found a bijection between n, so the natural numbers, and q, the rational numbers. The exact way that you form these pairings is quite clever, and it's too much for the margins of this video, but I'll link a video to Trevor Bassett on this topic. Let's imagine that you take all of these here on screen, you put them in a bag, you throw them at Cantor. He'll tell you these are all countably infinite sets. He would say that these are all the same size. Now, because he's a mathematician and wants no ambiguity, he discarded that 8 symbol, that upside down or sideways 8, and instead called it Aleph-Null. The reason is, well, Curt, if all infinities are equal, then why do you have to invent a new symbol? The answer is that not all infinities are equal, even though intuitively they are. So let's think about this. If you add 157 to infinity, you just get infinity. Same if you do infinity minus 157. So what number, outside of infinity itself, can you add or take away from infinity to give you something other than infinity? It turns out this is the defining property of infinity. This is actually my favorite definition in all of math. I remember hearing it for the first time and it blew my mind in that it's so unintuitive, but it's so darn brilliant at the same time. Something is infinite if you can take a finite amount away from it and it doesn't change size. I subscribe to The Economist. Their science and their AI coverage is among the best I've found anywhere. And I say that as someone who reads plenty of it. I'll give you some examples. They just ran an analysis on how attitudes towards science are changing in American politics and what this means for research and funding in scientific institutions moving forward. This sort of high-quality reporting is fantastic. They even covered how dark energy may be weakening over time. Now, if that holds up, it completely changes our understanding of the universe's fate. If you watch this channel, those are exactly the kinds of questions that we explore every week. I subscribe to The Economist because their science and their AI reporting regularly surprises me with how deep it goes. And they're also, of course, known for global affairs, both political and economic reporting. They are top tier, and interestingly and flatteringly, Toe is one of the only podcasts that The Economist partners with. So as a listener, you get an exclusive 35% off. That's not a deal that they have just anywhere. Head to economist.com/TOE to subscribe. That's economist.com/TOE for 35% off. Later on, Cantor proved that the real numbers, that R that you've seen, cannot be paired with the natural numbers. So R is not countably infinite. The argument is a proof by contradiction and uses something called diagonalization. You may have heard this. And I'll show on screen here where you just list all of the real numbers that you think are all of the reals in a column. And then via this diagonal construction, you'll find a way to build another number that wasn't in your initial list. Thus, your list wasn't complete. Thus, you have a contradiction by assuming that the reals were countable to begin with. I know I glossed over that, but I'll put more links in the description. The cardinality of the reals is written as 2 to the power of Aleph-Null. Now, that's quite wonky. Like, why 2 to the power of Aleph-Null? Why not call it Aleph-1? Now, it turns out that's precisely what the continuum hypothesis is. Is it the case that 2 to the power of Aleph-Null is equal to Aleph-1? We'll get to that. So each number can be expressed as a binary. I'm sure you've heard this. And real numbers are no different. You can think of them as an infinite sequence of zeros and ones. The collection of all such functions has cardinality 2 to the power of Aleph-Null. And the reason is just, I can ask you, well, what's in the first digit? And you could say either 0, 1. I could say, what's in the second digit? You could say either 0 and 1, and so forth. So you have 2 options for the first one, 2 options for the second one. And since real numbers go on to infinitum, then you have 2 to the power of Aleph-Null. But there's nothing deep about 2 here. Sorry, dualists. The base doesn't matter. You can go to 3 to the power of Aleph-Null. You could say 7. We could say 157 to the power of Aleph-Null. You can even do Aleph-Null to the power of Aleph-Null. It's still the same cardinality of the reals. Here's something that genuinely disturbed me. It still disturbs me, if I'm honest. The real line has exactly as many points as the complex plane. And R squared is the same cardinality as R, and R to the 100 is the same cardinality as R. Cantor himself wrote to Dedekind, I see it, but I don't believe it. So how do you get more infinities? Remember earlier I said there was some method of infinitely producing infinities. Cantor, along with someone else whose last name is Hartog, discovered that there's at least 2 machines for manufacturing larger and larger infinities. And they work by entirely different mechanisms. So machine number 1 is something called a power set construction. And that's actually what I used earlier in a sense. I mean, I didn't make it explicit, but that method of going from the natural numbers to the reals and showing the cardinalities 2 to the power of Aleph-Null, that's a power set construction. It just means you count all of the possible subsets of a set. And it turns out that all the subsets of a set equals 2 to the power of Aleph-Null. Don't worry about exactly why. The point is that that's machine number 1. Machine number 2 is, well, just define Aleph-1. Remember you were asking, well, why is it that we said 2 to the power of Aleph-Null and instead of calling it, say, Aleph-1? The answer is that we're going to call the next possible infinity Aleph-1 from Aleph-Null. And then the next one after that, we're going to call Aleph-2. Now, of course, you may be thinking, well, why am I making it into these discrete Aleph-Null, Aleph-1, Aleph-2? How do we not know there's a continuum, a smeared amount of infinities? And that's a great question. It's a tricky question, and Cantor asked it as well. He said, how do you know if the first step of machine 2 equals the first step of machine 1? In other words, is 2 to the power of Aleph-Null equal to Aleph-1? And that's the continuum hypothesis. You've worked your way across thousands of years of human history in something like 1,200 words so far. I think that's the cardinality of the word count. Now, also, I should have said that Hartog's machine number 2 produces a concrete way of getting discrete infinities. It's not a continuum of infinities. There's a theorem. But either way, it's quite cool that a 1,200 rung ladder can lead you to infinity. Now, there's so much more to say. like how the continuum hypothesis was the first problem in Hilbert's famous 1900 list, and how Gödel showed that you can't prove the continuum hypothesis from the standard axioms of set theory of ZFC. And then in 1963, Cohen showed that you can't prove it either. So you can't disprove it, you can't prove it. So this means that the continuum hypothesis is actually independent of ZFC. It's super wild that there exist statements that are independent. And this is worth a video of its own. And by the way, I talked about what independence means in the context of Gödel's work. See here in my video about misinterpretations of Gödel's incompleteness theorem. And by the way, many people don't realize that Gödel's theorem implicitly relies on infinity. And the reason is that you have to model piano arithmetic. Anyhow, all of this is extremely abstract, yes, but paradoxically, it's extremely concrete. Infinity is where the abstract and the concrete meet. Every construction here is specific and finite and checkable. Cantor's diagonal argument from earlier actually fits on a napkin, and Hartog's construction is an explicit recipe that you can follow and crank out infinities, step by step. Cohen and his forcing method is a technique that you can use. You can sit down and execute it, yes, with patience, with disgruntlement and Adderall, sure. Now, the objects being discussed here are infinite, but the reasoning about them is entirely finite, even mechanical. You know exactly what you're doing at exactly every step. Now, what I just said, the finitists would disagree. So not everyone accepts the output here. These finitists are mathematicians who reject infinity entirely. To a finitist, Aleph-Null is not a real mathematical object. It's at best a useful fiction. At worst, it's a symbol just pointing at nothing. Hilbert flirted, by the way, with a version of this position. A stronger stance is called ultrafinitism, and it goes even further. They would say that some super large numbers, like let's say 157 to the power 157 to the power 157, those are just suspect. There's no physical process that would ever instantiate something like this. It's an interesting melding of math and physics in a sense, these ultrafinitists. I spoke, by the way, to Dror Barnetton, who is an ultrafinitist, and I spoke to Norman Weilberger, who's a regular finitist. I'll put links in the description. There's also Nelson and Volpin, who I haven't interviewed, who have similar views like this. To an ultrafinitist, asking what is 2 to the power of Aleph-Null is like asking, what's the orange about jumping? It's a question of nonsense. Although I think I heard a Torontonian on Jarvis Street having a cogent conversation starting with that question. Most working mathematicians find infinity indispensable. So Hugh Wooden, who by the way is one of the most important living set theorists alive, living, is someone that I'll be speaking with soon on the Theories of Everything channel. You can subscribe for that. He spent decades saying that the continuum hypothesis does have a definite answer. His position is that ZFC is just simply too weak to detect it, that you need some stronger axioms, large cardinal axioms. I believe this is called his ultimate L program. Now, to get even more trippy, if this wasn't enough for you, there's an interview with Emily Reel on infinity categories, where she presents infinity categories at the most basic level. It's still super challenging, though. Actually, I'm working on a book with Penguin Press, and I'll be covering infinity categories and Hugh Wooden's work in it. By the way, you may wonder, why can't you divide by 0? That's an elementary question, and it's a reasonable question. And it turns out that in projective geometry, which is what Roger Penrose uses for twistor theory, you can use a division by 0. And it makes sense when you take the complex numbers and you union them with infinity, or a point, but he calls that point infinity for a reason. Using infinity lets you make 1 divided by 0 perfectly well-defined statement. That's how useful infinity is. So let's summarize. The old view is that imagine you're counting and you do 1, 2, 3, 4, 5, 6, blah, 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 blah. You never stop. You don't arrive at infinity. That's called a potential infinity. It's just a process that keeps going. We used to think that that's all infinity was. Then Cantor came along with Dedekind, and said, no, actually you can complete that whole set. You could treat it like a collection and do math with it. It's not a process anymore, or it's not only a process, you can treat it like a thing. That's called actual infinity. You can then ask the question that every guy is afraid a woman will ask them, how big is it? And you can compare it to other infinite sets. for instance, the reals. So you can compare the natural numbers with the reals, and you can show that they're not equal, and the reals has more than the naturals. And then you could also use another method called Hartog's method. So you can use machine 1 to produce the cardinality of the reals, and you could use machine 2 to produce a different set of cardinalities of infinities. And the question about how do these two machines relate at their lowest level, at their first level actually, is called the continuum hypothesis. Many people state it as, is there an infinity between the natural numbers cardinality and the real number cardinality? And of course, all of this has to be caveated because of those persnickety finitists and ultrafinitists who just say all of what you're speaking about is either a useful fiction, it's just somehow useful for you to do some computations, but doesn't actually exist, or, and that's the best case, or it's just nonsense. You're just speaking baba liba do bada, whatever, meaningless, grammatical, seemingly correct strings of symbols, but they don't refer to anything. And interestingly enough, the finitists and ultrafinitists do have a coherent philosophical position. I like it because it forces you to ask, what the heck do you mean when you say that some mathematical object exists? So, the debate is alive, and depending on your view, the fact that it's a debate at all, that mathematicians can disagree not about whether a proof is valid, but whether about the objects that the proof discusses even exist, that tells you something unsettling about the foundations on which the rest of math sits.